Hi everyone, it's Dr. Greenberger here to go through the kinetic molecular theory of gases. So let's go ahead and get into it. The kinetic molecular theory of gases is a tool that we use to describe the property of gases. We'll look at some of the key tenets of this theory, and then we'll look at how kinetic energy is involved and how temperature and molecular weight of the different molecules impacts that value. We'll look at a distribution of the speeds that different gas molecules can occupy and look at a way to graph those speeds. And then we'll calculate those speeds for a given gas at a given temperature. And then we'll look at two different ways gas molecules can move called effusion and diffusion, and think about a way to compare different gas molecules' effusion and diffusion rates. Okay, so we know that we've all experienced gases. They're surrounding us currently. We have oxygen and nitrogen, some CO2, etc. around us. And some tenets of being a gas means that your collection of atoms or molecules that fill the entire container exert some force called pressure, have very low densities, there's lots of space between gas molecules, and can be compressed. And we can see a schematic at the bottom here where we see those boxes where we have gas molecules separated and bouncing around with each other. And here we can see liquids where they will kind of take the shape of the container that they're in, but not completely fill them. And then we have solids, which take their own rigid shape within the container and are very dense. And so what we say for gases is that their kinetic energy, or their amount of movement, way dominate over the intermolecular forces. So even though there might be some, dispersion forces, dipole-dipole moments, hydrogen bonding that could occur between the different molecules, they're moving so fast that they don't even notice those potential interactions with each other. Okay, and so our postulates for kinetic molecular theory state that molecules will move in straight lines in random directions. So I think this is pretty easy to understand. If you have some gases, they're just going to go straight until they hit something and in completely different random directions from each other. We also say that gas molecules are very small. So compared to the total size of the container, the gas molecules, whether they're molecules or atoms, take up a very, very, very tiny portion of that. And like we mentioned earlier, we'll say that their intermolecular forces are not playing a role in how they interact with each other, because they're moving so fast that their speed and that motion kind of dominates over intermolecular forces. And we'll also say that when those gas particles do bump into each other, we'll experience elastic collisions, and we'll look at those in a second. And then we'll say that the average kinetic energy is proportional to temperature. So as temperature goes up, kinetic energy also goes up. And the unit that we'll always use on temperature is going to be Kelvin. And I'll show you a way to easily convert between degrees Celsius and Kelvin shortly. Okay, so just really want to emphasize this idea that temperature is a direct measurement of kinetic energy. And so as one changes, the other is changing along with it. Okay, so as promised, we're going to look at elastic collisions. And so oftentimes we think about billiards balls as being representative of elastic collisions. And so we can see what happens when the cue ball hits these two pool balls. And we'll say that in this case, all the energy is conserved. Boom. Okay, so we saw the collision, right? And we saw that the direction of the balls changed when they hit each other. Okay. And their speeds also changed, right? The cue ball slows down and the other two balls sped up. And so we'll say in elastic collisions, the speed and directions can change. The total kinetic energy divided up between the three balls remains the same. Okay. And so we know kinetic energy is telling us all about movement, And so it's nice to have a way to graph the speeds of those particles as they're moving. And to do this, we use what we call Maxwell-Boltzmann distribution. And it has a curve that looks something like this, where on the y-axis, we have the percentage of molecules. So it's like basically a way to count how many molecules in a sample have a given speed. And that speed is on the x-axis. Okay. So we can see that the peak of this curve is around 400 meters per second. And so we can see that even though we have a given sample of some gas at some constant temperature, we have this distribution of speeds. There's not just one speed that all of the gas molecules have. We have an array of speeds that the gases can occupy and move around at. And so the way that we usually report kinetic energy, which is related to motion, is through temperature, as we mentioned before. So we'll go ahead and look at some more of these Maxwell-Boltzmann distributions. So we have this distribution of speeds that molecules can occupy. And so oftentimes what we talk about is kind of a fancy way to do the average of those speeds. And that's what we call the root mean square speed. So the words root mean square usually describe a fancy way to do an average. And so we have our fancy average speed, which we denote with U RMS. And that's going to correspond to the speed of a particle with the average kinetic energy of the entire sample. And of course, we have an equation to describe this, where we say that the RMS speed is equal to the square root of 3 times RT divided by M. And that is, of course, on the data sheet. And for this equation, we'll use temperature in Kelvin. And that R is going to be a fancy gas constant. And so in this case, we'll use 8.314 joules per mole Kelvin. And hopefully you can see that joules, which is in the units, is a measure of energy. And when we're talking about speed and kinetic energy, obviously we're talking about energy. So we want to incorporate some unit of energy in our equation. Okay, so looking for the joules can help you remember which gas constant to use in this equation, because as we continue our discussion of gases, we'll use different R values. Okay, and then we have that kind of curly M, and that corresponds to the molar mass of whatever gas we're looking at. And something that's a little bit strange about using this equation is that we need our molecular weight to be in kilograms per mole. Usually when we're working with molecular weight, we use grams per mole. For this equation, we have to do that simple conversion with a factor of 1,000 to convert to kilograms per mole. So if we look at this curve, we can pick out what the RMS speed for the sample is by looking for a point that's slightly to the right of the peak. And the reason that we look slightly to the right is just because this peak isn't quite symmetric. Hopefully you can see that there's a little extra area to the right. And so our root mean square average will be a little bit to the right also. So for this particular sample, we would draw our RMS speed point there. And we could estimate that to be about 490 meters per second. And we can use the RMS speed to help us think about temperature and kinetic energy. So we can kind of relate those three terms together by using the traditional kinetic energy equation, 1/2 mv squared. So if you look at the equation that's written there, we have 1/2 times our molar mass times our average speed squared. Okay, so we're still following that 1/2 mv squared format. And if you plug in the equation from above into that equation, you'll find that everything simplifies down to be 3/2 times r times t. So this can help us see mathematically how it is that kinetic energy is directly proportional to temperature. If we double temperature, we double kinetic energy, etc. Okay, so there's a fun app in the ebook that we can look at. So let's go ahead and pop over to that window, and we'll look at changing some things. Okay, so we have this graph here on the left, which is representing our Boltzmann distribution. We can see we have fraction of particles on the y-axis and the speed on the x-axis in meters per second. And then on the right, we have our box of different molecules, and they're just bouncing around. You can watch them collide. You can see how they change speeds and directions. And if you'd like to, you can trace the particle and sort of follow one around as it bounces and changes directions randomly. And so right now you can see how most of our speeds are below this 1,000 meters per second. And then on the right here, I have some different things I can change. I have the N of helium, which is a way of saying how many moles of helium are in my box, or something proportional to how many helium gas particles I have. Then I can choose to add on neon, which we'll do in a moment. And I can change the temperature and the volume of my box and see how pressure changes. So let's go ahead and increase the temperature and see what changes. Okay. So if we look at our plot on the left here, we can see the curve is much flatter now. And the reason that it's flatter is that we have the gas molecules kind of spread out more in terms of what speeds they can occupy. Now the particles are they have enough energy to reach more of like the 2,000 meters per second speeds. So we can see we have this broader distribution now that particles are going faster. And those faster particles are what are appearing red and orange in the box here. Okay, so let's slow them down a little bit. And now let's go ahead and add in some neon. So neon, if you look at the periodic table, is a bigger noble gas than helium. So the circles will show up bigger. But let's see what difference it makes in terms of the speeds. I'm going to add in neon. And I'm going to have it track a helium for a moment. You can see the helium really bouncing and zipping about. Now let's track a neon. Okay. Okay, so it is moving about still. So now this graph on the left is showing us the helium speeds. Let's look instead at the neon speeds. So here we can see that those bigger neon particles are moving much slowly compared to the helium. Okay. So I recommend finding this in the ebook. It's just in that, if you go to gases on the left and go to the kinetic molecular theory tab, it's one of the margin links there. So you can find and play with this on your own. And you can pay better attention to what happens to the pressure as you change different things also, which is kind of fun. Okay. But for now, let's look at the PowerPoint again. Okay. So if we were to look at the questions that are listed here, it asks us about the speeds of the helium atoms that we were looking at the beginning. And we could see that no, they weren't moving at all the same speed. We had that distribution, which is marked in a sample plot there on the left. The second question that they pose is, if we increase temperature, what happens to the speeds? And we saw those particles move more quickly. They're able to still occupy slow speeds, but also occupy faster speeds. And then when we added in the neon atoms, we were able to see that they moved much more slowly than those smaller helium particles. So we're able to change two things, and we can look at how those change the Boltzmann distributions here in the next couple slides. So here we're going to consider how temperature of just one gas would change the Boltzmann distribution. And so we have three different temperatures to consider for this nitrogen sample. We have 100 Kelvin, 500 Kelvin, and 1000 Kelvin. And then we have our red, green, and blue curves. Okay. So if we look at the red curve, we have a huge peak. That peak corresponds to percentage of molecules. And the percentage of molecules that's really high is corresponding to a slower speed. Whereas if we look at the flatter, bluer curve, now we don't have such a big peak, but our gases are able to reach higher speeds, get up to that 1500 or so meters per second. Okay. And so those gases that are moving faster would correspond to a higher temperature, whereas those slower gases would correspond to a lower temperature. So the red curve would correspond to 100 Kelvin, the green curve to 500 Kelvin, and the blue curve to 1000 Kelvin. So we can kind of reiterate what effect temperature would have on our average speed. So we'd say increasing temperature, as we've seen, increases our average speed. And if we were to look at kinetic energy, again, we'll say increasing temperature increases our average kinetic energy. Okay. So I think that's pretty straightforward. You just want to make sure you keep the y-axis and the x-axis separate and clear when you're looking at these curves. And then you have to be a little careful too not to confuse this style of graph with the next style of graph that we're about to look at. So let's go ahead and do that. Here we're going to consider what effect mass has on the Boltzmann distribution of different gases. So we have four curves for four gases: helium, neon, hydrogen, and oxygen. And they're all now at the same temperature. So before we had the same gas at different temperatures. Now we have different gases at the same temperature. Okay. So now we want to think about how mass of these different gases will impact their speed. And we saw with our little simulation that the heavier neon gas moved more slowly than the lighter helium gas. So the smaller gases will move fastest, and hydrogen here is going to be our smallest gas. It's a molecular weight of about 2 grams per mole, which is going to be lower than the other three options. So that will correspond to our fastest gas. When we're looking for speed, we look on the x-axis. So we look for where we extend our curve furthest on the x-axis, which would here be our yellow curve. So that would correspond to hydrogen. And then the red curve, which favors slower speeds, would correspond to our heaviest gas. So here we can see that oxygen, which has our greatest molecular weight of about 32 grams per mole, is corresponding to our slowest Boltzmann distribution. Okay, and then we just, order them in terms of molecular weight. And so if we look at RMSB, we'll say constant temperature, the greater the mass of the gas, the slower the gas is. But because these are all at the same temperature, they all have the same average kinetic energy. So that can be confusing because we see the hydrogen moving faster. but it's still going to have the same kinetic energy as oxygen because they're at the same temperature. So if we look back at our previous example, here they do not all have the same kinetic energy because they each have a different temperature. Okay, so that can be a little bit of a sticky point. So just make sure when you're looking at these graphs, you take time to consider what your two axes are and to think about whether you're looking at changing mass at constant temperature or if you're changing temperature all for the same gas. Okay, but once I think you get those points clear, it's pretty easy to rank the curves from each other and put some things in order. Okay, and so just a reminder that for kinetic energy, we can go ahead and take that 1/2 mv squared form, where instead we use molecular weight and RMS speed. And so if we increase our mass, but have a constant kinetic energy, our RMS speed would have to be decreased. Okay, so if one of those two terms goes up, the other one goes down. So here we have a sample problem where we have 5 different gases with helium, argon, chlorine, hydrogen, and methane. And they want us to pick out the RMS speed for argon at this temperature. Okay. So in this case, they all have the same kinetic energy because they all have the same temperature. And what we're looking at is just different masses. Okay, so here we have our options for the potential RMS speeds. And so our first step is to go ahead and label each curve for whatever gas it would correspond to. And so all we did was say the graph that favors the left and the slower speeds will correspond to our heaviest gas. And if you use the periodic table to figure out the molecular weights of all of these 5 gases, you see that chlorine is heaviest, and then argon is heaviest, and then eventually we get to methane, helium, and hydrogen is the lightest. And so then once we have our 5 gases matched up with their plots, we can focus on the argon plot. And we know the RMS speed is going to be just a little bit to the right of the peak. And if we kind of follow that down, we can see that we're a bit shy of 500 meters per second. And that would correspond to answer choice B then, of 432 meters per second. And so here I have a worked out problem for how to determine and calculate the RMS speed for a given gas at a certain temperature. And so in this example, I have argon. And if you look at the molecular weight on the periodic table for argon, we can see that it's 39.963 grams per mole. And that'll be true at any temperature. But they say that the temperature of our sample is 310 Kelvin, which is body temperature. And so we'll start with our RMS speed equation, which is the square root of 3 times R times T divided by M, and we'll use our temperature in Kelvin. So for future reference, to figure out what the temperature is in Kelvin, you can take your degrees Celsius and just add 273 to it. And then if you want to do the reverse, you can start with your temperature in Kelvin and subtract 273. So that's how I knew this was body temperature. I took 310 Kelvin, subtracted 273, which is 37 degrees Celsius. Okay. So anyway, getting back to the problem, we have our equation, we have our temperature in Kelvin, which is good news. We'll need to use our gas constant, which is 8.314 joules per mole Kelvin. And seeing the Kelvin in that gas constant can help us remember to put our temperature in Kelvin. because we'll need those units to end up canceling out. And then we'll need our molecular weight in kilograms per mole. So the reason we need kilograms is that kind of hidden within the unit of a joule, there's kilograms in there. Okay, so that can be a really easy step to forget. So just try to make a note of it, print out your data sheet, and write what units you need next to it for future reference. Okay, so all I did then below was to take the 3, leave it as is, put in the gas constant, multiply by my 310 Kelvin, and then divide by my molecular weight in kilograms per mole. And then when you go ahead and plug that in very carefully into your calculator, you can see that you have an RMS speed of about 440 meters per second. So the actual computation part of this problem is pretty simple, but you really have to be careful to make sure all of your units and orders of operations are correct. So our last component of this discussion is the difference between effusion and diffusion. So I think these are terms that we've heard before, but a formal definition for effusion is when you have a gas that escapes through a tiny hole. So it would be like watching a balloon deflate. Sometimes it makes a funny noise. And diffusion is when gas is spread to occupy a volume. So this is like when someone in the corner of the room puts on some perfume and you can smell it on the other side of the room. So if we look at this box above, we have a container. It has a hole there in that blue wall, and we have it filled with these red gas molecules. If we were to watch one of those gas molecules escape through that hole, that would correspond to effusion. And so that's going to be different from diffusion, which is the case where we have kind of 2 gas samples, one represented with the red balls, one represented with the green balls. And we remove the wall partition or divider that's between them, represented by this blue partition. Then they're allowed to freely mix and spread out. And this is what we'll call diffusion. So these are 2 fairly common ways that gas molecules move about. And so we want to be able to kind of describe this and compare different gas molecules to each other mathematically. And to do that, we'll use what we call Graham's law. And so here I've laid out the derivation for Graham's law. It's actually pretty simple. This might look like a lot of variables on one slide. But all you do is start with the RMS speed equation for one gas with its own mass and divide it by the RMS speed for a different gas. Okay, and if you kind of simplify down to put them all under the same square root, we can see that the 3RT is the same for both of them. And so we can cancel that out and simplify it down to just have a 1 on top for both of them. And then instead of having 1 over divided by 1 over, we can flip the inside of that square root and end up with our final equation for Graham's law, which is going to correspond or relate the 2 effusion rates marked by R1 or R2 to their molecular weights and how those compare. So I have that same equation here. So this is Graham's law. This is also on the data sheet. And so so we know in the equation that we are using rate. Sometimes what they'll give you is the time for gas to diffuse or effuse. And in that case, sometimes we do have to convert from time to rate. So we just want to kind of give you a heads up about that. You'll see a worked out example of that in the homework. Okay, and in the ebook. But let's go ahead and compare how propane diffuses to some mystery gas. So they tell us that they measure the rates of propane and our mystery gas as they effuse through some hole. And they see that our mystery gas moves 1.66 times faster than the propane. So right away, I know something about our gas without doing any math. Since it's faster than propane, I know it must be lighter than propane, because we're going to assume they're both at the same temperature. And so that can be useful when you're doing multiple choice questions also, to kind of keep that in mind, because we know it's going faster, it must be smaller. Okay, but we can use Graham's law to actually identify the gas by determining its molecular weight. So here we have some options for what the gases could be. So we can start by getting our molecular weight of propane and converting that to kilograms per mole, since that's the unit that we use for RMS speed. We can start with our Graham's law. And since propane is heavier, I like to make it R2. You'll get the same result regardless of whether you make it R2 or R1. But then we know R1 is going to be 1.66 times faster. Okay, so if we call X the value for propane, then R1 will be 1.66 times X. And we can plug it in like this, where we put in our propane's molecular weight and just leave M1, what we're going to solve for, which is the molecular weight of our unknown. Our X's cancel. And so then to solve for M1, what we'll have to do is take the square of both sides to cancel out the square root. And then we can multiply our M1 over and divide by that 2.76. And that value we solve for M1 will be the mass of our unknown gas given in kilograms per mole. So then to answer the question, we're just going to go ahead and match that mass up to one of the 5 answer choices. And we'll find that this corresponds to methane. So we can use the rates of gases to determine the identities of mystery gases, or maybe we could kind of have some sort of race between 2 gases and say if this one weighs this much and this one weighs this much, how many times faster will the faster one move? And we'll know, of course, that the faster gas would be our lighter gas. Okay, so with that said, here we have our 5 postulates of KMT. So just to review quickly, we know gases move in straight random lines. They're really small compared to the container. They don't attract or repel each other. They're moving so fast that they don't even notice whether they attract or repel. And when they do collide, they keep the same amount of total energy between them, though their speed and direction may change. And then we've really tried to emphasize that temperature is a direct measure of kinetic energy. And if one goes up by some amount, the other will go up by that same factor. So our lecture on Friday will be a further discussion of gases. We'll talk more about volume, pressure, temperature, the number of moles of gas we have, and all of that good stuff. So be sure to like, subscribe, share, and we'll see you all again soon. Thanks for making it to the end, and good luck.